Hello. In this video, definition of derivative part 3, we're going to round off our understanding of the derivative by looking at an important question. What does it look like to be differentiable? Now, we know what it looks like to be continuous. That means connected. So, for example, a graph like this would be continuous, and a graph like this would not be continuous. But what does it look like to be differentiable? What does it look like to have a tangent line? Well, we know, for example, that functions like x squared and root x, we know they're differentiable. And so what is it about them that makes them differentiable where maybe other functions maybe aren't? How does it look to have a tangent line or to not have a tangent line? And in particular, could we at least say that it's maybe connected? If a function is differentiable, if it has a derivative, if it has a tangent line, does it feel like that function should at least be connected? We might not know other things about the function, but surely something like this where it's not connected here, there could be no tangent line. If you're going to have a tangent line there, you certainly must have to have a connected graph. And indeed, that's a theorem that we can go ahead and prove. The theorem states that if f is differentiable at a, then f is continuous at a. We get this idea that if a function is differentiable, if it has a tangent line, then surely it's connected. Surely it's continuous. Now, just to recall, to be continuous means the limit as x approaches a of f of x equals f of a. That's the definition of being continuous. And so we're going to need to use that in our proof. Because if you notice, these are both English statements, and we're going to need to convert them into math statements to work on them and use some algebra. So let's look at the proof. We're going to start off by assuming the beginning. We're told that if f is differentiable, so we should suppose that. Suppose fx is differentiable at x equal to a. Well, what that means is the derivative exists. So, therefore, f prime of a, which we could write as the limit x approaches a, and we're going to do the first definition, f of x minus f of a over x minus a. This limit exists. Okay, well, that doesn't really help me because I want to show not that this limit exists, but I want to show that this limit exists, the limit of f of x, and I want to show that it equals f of a. Well, to do this, we have to take a step back. We have to consider the limit as x approaches a of something different, of f of x minus f of a. Now, if you were to plug in a, you would get f of a minus f of a, which of course equals 0. So we expect this limit to equal 0, but remember, we can't plug in a because that's what we're trying to prove. We're trying to prove that you're allowed to plug in a, that the function is continuous. So what can we do instead if we're not allowed to plug it in? Well, there's a little technique here, a little insight or trick, if you will. We could multiply and divide by something. What about x minus a? Again, in math, you're always allowed to multiply and divide by something. So let's go ahead and multiply and divide by x minus a. Now, if we do that, notice that this portion looks like this limit we have right here. Well, that's good because this limit exists. And here we have x minus a, which is just a polynomial that we can evaluate. And of course, we have multiplication here. And we know that we can separate limits using limit laws. So this will be the limit x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a. And the reason we're allowed to do this is by the limit law. By the limit law. In particular, the one that the limit of a product is the product of the limits. So that's our justification for that step, okay. Well, let's go ahead and look at each one of these limits. The first limit, we know it exists. It equals f prime of a. And the second one, because it's a polynomial, we're allowed to just plug it in as a minus a. Well, a minus a is 0, so we have f prime of a times 0, which is just 0, like we expected. All right, so we've shown that the first part is equal to 0. So now we're going to consider the limit x approaches a of f of x, our original question. We want to plug this in, but again, you can't plug it in. That's what you're trying to prove. Well, we can do another sneaky thing in math. In math, you're always allowed to add and subtract anything you want. So what if we add and subtracted f of a? Well, notice, this portion here, f of x minus f of a, we just considered that limit. And when we considered that limit, we found that it was 0. So let's go ahead. We can split this limit up as the limit x approaches a of f of x minus f of a plus the limit x approaches a of f of a. Again, we're allowed to do this because of the limit laws. We know that the limit of the sum is the sum of the limit. So we can say, by limit law, limit of sum is the sum of the limits. Okay, well, the first limit there, we just figured out from above, was 0. The second limit is a constant. F of a is just a constant. The limit of a constant is the constant itself. So we get f of a. 0 plus f of a is f of a. So we've just shown that the limit of f of x as x approaches a is just f of a, which is the definition of being continuous. So we can say, therefore, f of x is continuous at x equal to a. And we put a box because we've completed our proof. Now we need to look at some of the logic here because this stuff is a little tricky for people to understand, especially when we haven't had a lot of training in logic. So we're going to take a step back before we talk about the continuous and differentiable. Let's think about some humans. If you are a human, then you are mortal. Is this statement true or false? Mortal means, unfortunately, that at some point you'll pass away. So if you are a human, then at some point you will pass away. Is that a true or false statement? Well, I think we would all agree. It's sad, it's maybe a little bit morbid, but that statement is true. Let's look at the reverse, though. What if we just switch that around? If you are mortal, then you are a human. Is that a true statement? If you're mortal, then you're a human. Well, I don't think so. That seems kind of false. What about a squirrel? Let's think about a squirrel. Is a squirrel immortal? Well, yeah, squirrels, they tend to die as well. They don't live forever. They're not immortal. Squirrels are mortal, but squirrels are not humans. So the squirrel clearly shows that this statement is false. Because there are many things that are mortal that are not human. So the statement, if you are mortal, then you are a human, that is not a true statement. If you were to diagram it out, what happens is that humans are inside here, and mortals are inside of here. So all humans are mortal, but not all mortals are human. They're not the same thing, and so you can't go switching the statement around. Now let's go ahead and look at it in the context of calculus. If you are a differentiable function, then you are continuous. Is that a true statement? Well, let's think about it. If you're differentiable, are you then automatically continuous? I think so. I think that is true. That is definitely true. We just proved that that was true. 100%, 100%. But if you are a continuous function, then you are differentiable. If we switch it around, is that true? If we just go ahead and switch those around, is every continuous function differentiable? Well, it feels like maybe no, because we set it up above that it shouldn't just flip around. But to show that this statement here was false, I needed to produce a squirrel. The squirrel was what showed that there are mortals that are not human. So what's the squirrel in our context? What's the mathematical squirrel that we need? Well, we need a function that is continuous, but that is not differentiable. That would be our squirrel that would show that this is false. So I'm pretty sure this is false, but we need a squirrel. We need a function that is continuous, but not differentiable. Let's consider f of x equal to absolute value of x, which remember is either negative x when x is less than 0 or x when x is greater than or equal to 0. Now, is f of x continuous at 0? I mean, it seems continuous. If you imagine the absolute value function, it sounds continuous, but let's go ahead and prove it. So we're going to find, of course, step 1, f of 0, which is equal to 0. Step 2, we'll do the limit x approaches 0 from the left. That means we'll take negative x, which gives us negative 0. Of course, negative 0 is just 0. Let's do the limit x approaches 0 from the right, which will just give 0. So clearly these are equal, and the limit as x approaches 0 overall of fx, in our case, absolute value x, is equal to 0. So step 3, the limit as x approaches 0 of fx equals f of 0, because 0 is equal to 0. So yes, we can say with absolute certainty, yes, the absolute value graph, absolute value of x, is continuous at x equal to 0. All right, is it differentiable? Is it differentiable at 0? Well, to do that, we can go ahead and try to calculate f prime of 0, which is going to be the limit h approaches 0 of f of 0 plus h minus f of 0 over h. You could do the whole derivative, but I'm just looking at the particular point where x is equal to 0. Now let's go ahead and work on this limit. So we'll get the limit h approaches 0. F of x we know is absolute value, so absolute value is 0 plus h minus absolute value of 0 over h. So it'll be the limit h approaches 0 of absolute value h over h. Now, to do this function, remember that the absolute value is technically a piecewise function. It's either h or negative h, depending on if h is positive or if h is negative. Which means as we plug in h approaching 0, well, what do we put for absolute value? So what do we put for absolute value of h? Do we do h? Do we do negative h? It means we have to do limits from either side. So we'll do the limit h approaching 0 from the left. If we do that side, we're going to get the limit h approaching 0 from the left. H is going to be less than 0, so we're going to get negative h. We can go ahead and cancel those h's, which will give us limit h approaches 0 from the left of negative 1, which is negative 1. If we do the limit as h approaches 0 from the right of absolute value h over h, that means h is taking values greater than 0, so we just get h. We cancel those out, and we get the limit h approaches 0 from the right of 1, which is just 1. But, and this is very important, these are not equal. So therefore, over here, the limit as h approaches 0 of absolute value h over h does not exist. Well, that was our whole question. That was the derivative at 0. So if the limit doesn't exist, we can say again, therefore, f prime of 0 does not exist. And if the derivative doesn't exist in English, that means f of x is not differentiable. Fx is not differentiable at x equal to 0. It's not differentiable. It doesn't have a derivative. So we found our squirrel. We found our function that is continuous but not differentiable. Now let's look at what this looks like on a graph. So here we have the absolute value function, and you can see very clearly that it is continuous. It's connected. But it's not differentiable at 0, and you can start to see that. Try to imagine drawing a tangent line at 0. Do you think the tangent line would look like this? Do you think it would look like this? Do you think it would look like this? There's all sorts of different tangent lines you could draw. And because of that, there's no single tangent line. There's no well-defined line you could draw off of that point. That sharp point makes it impossible to draw a tangent line. And so the failure to be differentiable, it looks like a sharp point on the graph. Anytime you see a sharp point, it means the function is not differentiable. And so this is very, very important. Not all continuous functions are differentiable, right? Not all mortals are human. Just because a function is continuous doesn't mean it's differentiable. If it's differentiable, certainly it's continuous, but not the other way around. And in fact, it's not just that functions are sometimes not differentiable, maybe at a particular point. There was a very famous mathematician named Karl Weierstrass who invented a very interesting function I want us to take a look at briefly. So in mathematics, the Weierstrass function is an example of a real valued function that is continuous everywhere but differentiable nowhere. It's an example of a fractal curve, and it's named after its discoverer, Karl Weierstrass. So what he did was he had this crazy looking function. If you notice, it's connected, but it's infinitely sharp and pointy. No matter where you zoom in, it continues to get sharper and sharper and pointier. So jagged is this function that it is actually never differentiable. There's not a single point on which you could draw a tangent line. And it was a very, very famous example because it was first published in 1872, and it illustrated that you could have functions that were bizarre. In fact, it was called a pathological function, almost like an evil or a sick function, because it was such an affront to what the mathematicians at the time believed. Henry Poincaré famously described them as monsters, and he described Karl Weierstrass's work as an outrage against common sense. But of course, these functions were very sensical and very important. They did not gain widespread acceptance until later, when they were introduced to help model Brownian motion. And so this function, while initially was ridiculed because it was almost like an evil and sick function, it ended up being incredibly useful in mathematics. So it's important that you think about the idea of being differentiable. If it's not differentiable, then that means it's going to be sharp and pointy. So if you're looking for it to be differentiable, you're going to look for it to be smooth. Now let's do a quick multiple choice question here. Which of the following functions is differentiable on the entire interval in view, either a, b, c, or d? All right, the correct answer is b, and we'll go through why. For a, you have a sharp point there. For c, you have a sharp point. And for d, you're not even continuous, not connected. Remember, if a function is differentiable, it certainly must be continuous. But here, it's connected the whole time, and it's smooth the whole time. Again, that's what you're going to be looking for. You're looking for a function to be smooth if it's going to be differentiable. Now just take a guess. At what point do you think the function f of x equals absolute value of 3 minus x is not differentiable? Negative 3 and 0, 3 and 0, 0, 0, or 1 and 0. All right, so the correct answer is B at 3 and 0, because the absolute value of 3 minus x is going to be moved over 1, 2, 3 to the right, and it's still your typical V shape. So the point where you have the problem is at 3 and 0. Before we end this video, I want to pose you a problem to work on. We'll show the solution for this problem in the next video, but until then, I want you to try it yourself. Give it a little bit of thought, a little bit of effort. We know that if our function fx is x squared, then the derivative is equal to 2x. We proved that on the very first day of class. And if our function is x cubed. Then in this series of videos, we were able to show that the derivative is 3x squared. So what do you think would happen if the function was maybe x to the 4? Do you have a suggestion, a prediction on what the derivative would be? Well, I'll give you some help. The answer is going to be 4x cubed. And so the question is, if you had a function of just x to the power of n, what would the derivative be? And if you can come up with that formula, can you prove it? Can you find a proof? Using the 3 steps, step 1, step 2, step 3, with fx plus h and fx plus h minus fx and so on. Is there a way to not only guess at this rule, this pattern, this formula, this connection, but is there also then a way to prove that that rule is true? I'll leave you with that to ponder, and feel free to give it a try. As a hint, you might need to use the binomial theorem. So for homework, you can try some questions on page 162, 1, 3, 21 to 31, and 41 to 44. Hopefully you enjoyed this video, and as always, thanks for watching.